Welcome. Today we will see Chapter 2, Representation of Control Components. Now we will see syllabus. First of all, we are going to learn mechanical elements such as helical spring, viscous damper, torsional spring and damper. Then we are going to learn electrical elements, that is resistor, inductor, capacitor, series and parallel electrical and mechanical elements, grounded chair representation. Then we are going to study analogies. Analogies means similarities. In that we are going to study direct and inverse analog for mechanical, thermal and fluid systems. Afterwards, we are going to study linearization of non-linear functions and linearization of operating curves. Therefore, first element we are going to study is helical spring. It is a mechanical element. Now you are seeing in the diagram that helical spring is there and a force Fs is applied on the spring so that spring is getting compressed by distance x as shown in this load deflection diagram. Now we are knowing that when a force is applied on the spring is getting compressed. Therefore, spring will offer resistance to its compression, and that resistance is known as spring force. Therefore, the spring force Fs required to deflect a spring a distance x from its free length is given by equation Fs is equal to kx. Therefore, Fs is nothing but spring force and k is equal to spring constant or stiffness of the spring, and x is equal to deflection of the spring. Therefore, you can represent this equation, that is Fs is equal to kx, by using the following block diagram. Now how to read this block diagram? Fs into 1 upon k is equal to x, because from this equation Fs is equal to kx, you can write x is equal to Fs upon k. Therefore, that you can represent by using this block diagram. Next component, that is viscous damper. Therefore, this is the diagram of the damper. Viscous damper is nothing but our shock absorber. We are knowing that in the shock absorber there is a damping fluid and spring is there, and shock absorbers are used to absorb the shock. Shock means force. Shock absorbers are used in the two-wheelers, four-wheelers. Also, shock absorbers are finding many applications in case of vibration isolation. Therefore, in case of viscous damper, this is the piston which is reciprocating inside the cylinder, and the displacement of the piston is given by x. Now in between piston and cylinder, here in the space, here damping fluid or viscous fluid is there, having damping coefficient as B. Now this FD indicates damping force which is applied on the piston. Therefore, when FD is applied on the piston, therefore piston will reciprocate inside the cylinder with certain velocity V. Therefore, you can write that for a viscous damper shown in the figure, the force FD required to move one end of the dashpot at a velocity V relative to the other end is equal to the product of the damping coefficient V and the velocity V. Therefore, FD is equal to B into V, which is equal to V into dx by dt. Therefore, you can write this equation as FD is equal to B dx, where capital D is equal to d by dt. Therefore, you can write this equation, that is FD is equal to B dx, in terms of block diagram. Therefore, before seeing the block diagram, this equation FD is equal to B dx, you can write like this: x is equal to FD upon BD. Therefore, this is the block diagram of this equation. Therefore, how to read this block diagram? FD into 1 upon BD is equal to x. Now, next element, spring with successive load. Now, consider these diagrams A and B. Now, first of all, we will see diagram A. Now, in the diagram A, you are observing that one spring is there having suppose free length L. In the second diagram, a mass M is applied at the free end of the spring, so that it is having deflection delta St. In the second diagram, another force Fi is applied on the mass M, so therefore we are getting additional deflection Xi. Again, another force small f is applied on the mass M, therefore additional deflection small x we are getting. Therefore, total deflection of the spring from starting position to the last position is delta St plus Xi plus X. And how many forces are acting on this spring? This weight of the mass, that is mg, in the downward direction, this force Fi, and this small force F. Now, this diagram A has been replaced by diagram B here, in which small force F is acting on the mass M. Therefore, mass M is going to move in the downward direction X, and spring K is also getting compressed. Therefore, whatever it is written here, I have told you, I have explained the things. Therefore, the summation of the total forces acting on the mass is mg plus Fi plus F minus K into bracket delta St plus Xi plus X is equal to md square into bracket delta St plus Xi plus X is equal to md square, where delta St plus Xi plus X is the deflection of the spring. The reference position is the equilibrium position in which the deflection due to mg and Fi is delta St plus Xi. The fourth equation at this reference position is mg plus Fi minus K into bracket delta St plus Xi is equal to 0. Therefore, subtracting the equation for the forces at the reference position from the equation for the total forces yields F minus Kx is equal to md square x. Therefore, consider again this diagram, how this equation came. F minus Kx is equal to md square x. Suppose this force F is acting on this mass M. Therefore, mass M is going to move in the downward direction. Therefore, spring will get compressed here. Therefore, mass M is going to move in the downward direction because of this force. Therefore, this mass is going to accelerate in the downward direction. Therefore accelerating force will be in the downward direction. Now we are knowing that accelerating force is equal to mass into acceleration. Therefore this accelerating force on the mass is acting in the downward direction, that is MA. MA means what? md square x, or m into d2x upon dt square. That d2 divided by dt square we have replaced by d square. Therefore md square x accelerating force is acting in the downward direction. Now opposite to that accelerating force, inertia force will act on the mass m, which will act in the upward direction. Now we are knowing that accelerating force and inertia force are equal and opposite. Therefore md square x, that is inertia force, will act in upward direction. And the spring force kx, spring will resist its deflection. Therefore spring force kx will also act in upward direction. Therefore making summation of the forces, how many forces are acting? External force F, spring force kx is in the upward direction, and inertia force md square x in the upward direction. Therefore this equation will become F minus kx is equal to md square x. Therefore by shifting kx towards right side and taking out common x, therefore we can write F is equal to md square plus k into x. Therefore this is the block diagram. How to read this? F into 1 upon md square plus k is equal to x. Now next, see this diagram. This mass m is there. It is supported by spring k and damper b. External force F is acting on the mass m. Therefore mass m is going to move in the x direction, in the downward direction. Now we will draw its free body diagram. This is the free body diagram of the mass m, on which it has been shown that how many forces are acting on the mass m. Therefore this external force small f is acting in the downward direction. Now because of this external force f is acting in downward direction, spring is getting compressed. Therefore spring force kx will act in upward direction. Similarly this damper is getting compressed. Therefore damping force is nothing but bdx. bdx will also act in upward direction. And since this mass m is going to move in the downward direction because of this force F, that is mass, because of this force F, accelerating force will act on this mass m. Accelerating force, we are knowing that accelerating force F is equal to ma. Therefore a means d2x upon dt square. Therefore m acceleration is equal to md square x. Now we are knowing that accelerating force and inertia force are equal and opposite. Therefore inertia force will act in the upward direction, which is equal to md square x, because accelerating force is acting in the downward direction. Therefore making summation of the forces, we are going to write down the equation F minus kx minus bdx is equal to md square x. Therefore shifting this kx and bdx towards right hand side, we can, and taking x common, we can write F is equal to md square plus bd plus k into x. Now this is the block diagram. How to read this? F into 1 upon md square plus bd plus k is equal to x. Now next point, torsional spring and damper combination. A disc rotating in a viscous medium and supported by a shaft is shown in figure. The applied torque tending to rotate the disc is T. Therefore this is the figure. This disc is there. Disc is attached to the one end of the shaft. T is nothing but external torque applied on the disc. Therefore this disc is there in the viscous medium. Therefore because of this torque T, there is some angular displacement of the disk will be there. Angular displacement is given by theta. Therefore, because of this torque T, shaft is going to be twisted in clockwise direction, because this torque is acting in clockwise direction, and this disk will also rotate in clockwise direction. Therefore, shaft will resist its deflection in clockwise direction. Therefore, shaft torque Ts will act in anti-clockwise direction, and this damping torque Td will also resist the motion of this applied torque. Therefore, damping torque Td will also act in the anti-clockwise direction. Now, this applied torque T is also known as accelerating torque. Now, opposite to the accelerating torque, here inertia torque is also acting in the anti-clockwise direction on this disk, and that torque is nothing but T, because applied torque or accelerating torque is equal to inertia torque. But therefore this torque is given by J into alpha. Therefore, the shaft torque and viscous friction torque oppose the motion, so that now summation of the torque is given by T minus Ts minus Td is equal to J alpha. This J alpha is nothing but inertia torque, which is equal to, we are knowing that alpha is equal to angular acceleration. Angular acceleration is nothing but d2 theta upon dt square. Therefore, that d2 upon dt square is replaced by d square. Therefore, it is inertia torque is given by j d square theta. Therefore, where j is equal to mass moment of inertia of the disk and alpha is the angular acceleration. Now we will find out separate values of Ts and Td, and we will substitute in this equation. The shaft torque Ts is given by Ts is equal to Ks into theta, and the viscous friction torque Td is given by Td is equal to Bv into d into theta. Therefore, Ks is equal to torsional spring rate, theta is equal to angle of twist, Bv is equal to coefficient of viscous friction. Therefore, by substituting value of Ts and Td, we are getting final equation, that is T is equal to Jd square plus Bvd plus Ks into theta. And this is the block diagram. How to read this? T into 1 upon Jd square plus Bvd plus Ks is equal to theta. Now we will see electrical components. Now there are basic three electrical components: resistance or resistor, inductor and capacitor. Therefore, first of all we will see resistor. Now this is known as the resistance or resistor R, and ER is the voltage drop across the resistor. Therefore, the equation of the voltage drop ER across resistor is ER is equal to RI. Therefore, you can represent this equation by using block diagram also. Therefore, R is known as resistance in ohm and I is the current flowing in ampere. Therefore, this equation you can represent in the block diagram like this: ER into 1 upon R is equal to I. Now next element, inductor. Inductor is represented by letter L. EL is the voltage drop across inductor. Therefore, the voltage drop EL is given by the equation EL is equal to L into di by dt. Therefore, EL is equal to L di, where capital D is equal to d by dt. This already we have studied. that is differential operator d is equal to d by dt. Therefore, L is the inductance in Henrys. Therefore, you can represent EL is equal to LDI by using the block diagram like this. EL into 1 upon LD is equal to I. Now, third element, that is capacitor. Now, capacitor is represented by letter C, and EC is equal to voltage drop across capacitor. Therefore, voltage drop EC across a capacitor is EC is equal to 1 upon C into integration of I dt. Therefore, we are knowing that integral sign is replaced by 1 upon d. Therefore, final equation we are getting as EC is equal to 1 upon CD into I, where C is the capacitance in farads. Therefore, EC is equal to 1 upon CD into I is represented by the following block diagram. EC into CD is equal to I. Now, we will study this RLC series circuit. Now, you just see three elements are there: inductor, resistor and capacitance. EL is the voltage drop across inductor, ER is the voltage drop across resistor, and EC is the voltage drop across capacitor, and E is nothing but total voltage drop across inductor, resistor and capacitor, and I is the current flowing through the circuit. Therefore, total voltage drop E is given by, now we are knowing that voltage drop across resistor is equal to ER is equal to RI, voltage drop across inductor EL is equal to LDI, and voltage drop across capacitor EC is equal to 1 upon CDI. Therefore, we can write down the equation E is equal to EL plus ER plus EC. E is equal to EL plus ER plus EC. Therefore, substituting these values of ER, EL and EC in this equation, we are getting E is equal to RI plus LDI plus 1 upon CD into I. Now, taking I common, we are getting the equation E is equal to EL plus ER plus EC is equal to LD plus R plus 1 upon CD into I. We have taken here current I as the common. Now, next, the charge Q is the time integral of the current, that is Q is equal to 1 upon D into I. 1 upon D is known as integration. Q is equal to integration of I. Integration sign is replaced by 1 upon D. Therefore, I is equal to dq. Next, by noting that, therefore, LDI is replaced by is equal to LD square Q. Ri is equal to RDQ. And 1 upon CDI is equal to 1 upon C into Q. Just we have put this value of IDQ here in this equation, and we have got these three values. Therefore, voltage drop E is given by EL plus ER plus EC is equal to LD plus R plus 1 upon CD into I. This equation already we have studied. Therefore, substituting the values, we will obtain the equation of E in terms of Q. Therefore, E is equal to LD square plus RD plus 1 upon C into Q. and we will represent this equation by using the following block diagram. E into 1 upon LD square plus RD plus 1 upon C is equal to Q. Therefore, this is the RLC series circuit. Next, now we will see series and parallel laws. First of all, we will see series and parallel laws of electrical circuit. Now, elements are usually connected in either a series or a parallel arrangement. Arriving at the equation for such systems can be greatly simplified by the use of the laws of series and for parallel combinations. Therefore, first of all, we will see series electric circuit. Now, this is the series electric circuit in which two inductors L1, L2, two resistors R1, R2 and two capacitors C1, C2 are connected in series. E is the voltage, total voltage drop across these elements, and I is the current flowing through these elements. Therefore, already I have told, it is written here. Therefore, the equation for the summation of voltage drops is E is equal to EL1 plus EL2 plus ER1 plus ER2 plus EC1 plus EC2. Therefore, substituting the values of EL1, EL2, ER1, ER2, EC1 and EC2, we are getting E is equal to EL1 is equal to what? L1 into DI plus EL2, L2 into DI plus ER1, R1 into I plus what is the value of ER2, R2 into I plus what is the value of EC1, 1 upon C1D into I plus what is the value of EC2, 1 upon C2D into I. Therefore, taking current I common, this equation can be represented by E is equal to into bracket L1D plus L2D plus R1 plus R2 plus 1 upon C1D plus 1 upon C2D into I. Therefore, the equation relating the voltage E and current I for any electric circuit can be expressed in the form E is equal to Zi. Now, every time we have to use this equation, E is equal to Zi, where Z is the impedance of the circuit, E is the voltage drop across the circuit, and I is the current flowing through the circuit. Therefore, the impedance Z is given by Z is equal to L1D plus L2D plus R1 plus R2 plus 1 upon C1D plus 1 upon C2D. Therefore, for elements in series, total impedance is the sum of the individual impedances of each element. Therefore, the block diagram representation is shown in figure, that is E into 1 upon Z is equal to I. Therefore, this you remember, for series elements, the total impedance is the sum of the individual impedances of each element, because this we are going to use while solving the problem. Next, parallel electric circuit. Now here parallel electric circuit is shown in the figure. Two inductors L1, L2, two resistances R1, R2 and two capacitances C1, C2 are connected in parallel. Now, in case of parallel electric circuit, voltage drop E is same across each element, but current I is divided in between these elements. Therefore, you can write that total current I flowing into the system is the sum of the currents flowing through each element. Here in case of parallel circuit, current flowing through each element is different, but voltage drop E remains same. Therefore, I is equal to E divided by L1D plus E divided by L2D plus E divided by R1 plus E divided by R2 plus E divided by 1 upon C1D plus E divided by 1 upon C2D. Therefore, we will write equation E is equal to 1 divided by 1 upon L1D plus 1 upon L2D plus 1 upon R1 plus 1 upon R2 plus C1D plus C2D into I is equal to Zi, where Z is equal to 1 divided by 1 upon L1D plus 1 upon L2D plus 1 upon R1 plus 1 upon R2 plus C1D plus C2D. Therefore, for parallel elements, we can say that the total impedance is equal to 1 divided by the sum of the reciprocal of impedance of each element. That is written here. Total impedance for parallel element is equal to 1 divided by reciprocal of impedance of each element. 1 upon L1D plus 1 upon L2D plus 1 upon R1 plus 1 upon R2 plus C1D plus C2D. Therefore, the block diagram representation is shown in figure. Therefore, E is equal to Zi. Therefore, E into 1 upon Z is equal to I. Therefore, we will stop here. Thank you very much. Therefore, from this lecture, what we have studied? We have studied spring, helical spring, then we have studied viscous damper, then we have studied torsional spring and damper, then we have studied basic electrical elements, that is resistor, inductor, capacitor, then we have studied series electrical elements, that is series electrical circuit, and then we have studied parallel electric circuit. In case of series electrical circuit, total impedance is the sum of the individual impedances of each element, and in case of parallel electrical circuit, the total impedance is equal to 1 divided by sum of the reciprocal of the impedance of each element. Therefore, we will stop here. Please study this carefully, that is how to represent or how to write impedance of series elements and how to write impedance of parallel elements, because this we have to use while solving the problem. Thank you very much.